Hi there, welcome to module 11. In this module what we are going to do is we are going to learn minimization of what is called multiple output functions. So far we have seen several kinds of circuits. So just in the last module I introduced the notion of multiple outputs. Till then we had only single outputs, and even in the last module we looked at, for example, BCD incrementer. We had 4 values W, X, Y and Z, and we came up with expressions which are individual maps that are made one at a time. We made a map for W, we made a map for X and so on. So I am going to now make a case for minimization of multiple output functions, where you consult all the tables together and see if you can minimize the hardware. So let us look at this example. Let us say I have so I have 3 input bits that are coming in, namely A, B and C, and let us say I have a function. So I have 2 outputs coming from the circuit, one output called F, which is the sigma of 0, 2, 6 and 7, and another input called G, which is the sigma of 1, 3, 6 and 7, and we can go and put them in the K maps. So we have it here. So the one on the left side is for sigma 0, 2, 6 and 7, and the one on the right side is sigma of 1, 3, 6 and 7. Now you want to minimize this is something that you can do. For F, this is A bar C bar plus AB, so this is the term which is AB and this term is A bar C bar, and for G this term is AB and this term is A bar C. So we can go and implement them separately. We can implement them as 2 separate systems, one circuit for implementing F and another separate circuit for implementing G. If we did that, then we would have needed overall 6 AND or OR gates plus 3 inverters. So for example, you would have needed an inverter for A bar here, a C bar here, you would have needed another inverter for A bar here, because we did not share anything, we designed this as 2 separate circuits. Then you would have needed one AND gate here, one AND gate here, one OR gate here. Similarly, one AND gate here, one AND gate here and one OR gate here. We would have needed 6 AND or OR gates plus 3 inverters. But from the expression you can see that AB is actually common to both F and G, right. So it is probably apparent to you, because even in the min terms we have 6 and 7 which are common to F and G. So the 6 and 7 has in turn resulted in one term called AB, which is common to both, right. If we actually allow for sharing, then we can do something better. If we notice that AB is being shared, then we can do something better. So this is a circuit which allows for sharing. So in the top we have the function F, in the bottom we have the function G, and you have A bar that is given as input here and C bar given as input here. So that is A bar C bar, and this is AB. So A bar C bar plus AB is derived as F, and A bar C plus AB is derived as G. So we do not have 2 copies of the AND gate. So what is not shown is that A bar itself can be shared using just one inverter. We do not need 2 inverters for the expression on the left and expression on the right. We can use just one inverter. The inverter is not shown in this circuit. So if you throw in the inverter also, then overall we would have needed 5 AND OR gates plus 1 inverter. So with sharing we would have needed 5 AND OR gates plus so it is 2 inverters. C also needs an inverter because of C bar. So we need 2 inverters, I am sorry about that. So we need 2 inverters plus 5 AND OR gates. So clearly there is a reduction in the number of hardware circuits that we are using. So 1 AND or OR gate less and 1 inverter less. Again remember, in terms of cost, this has lesser cost and it has exactly the same functionality as designing it as 2 separate circuits. So clearly this is useful, and we would like to do this in a more systematic manner. So this is a simple example, we would like to do this in a more systematic manner. Let us see another example. So in this example what we have is, I have given you the truth table and the expressions here. So we have 2 1s here and a loner 1 here. So this gives us the term, A bar B bar, and this gives us the term A B C bar. So here we have 2 groupings of 2 each. So this vertical one gives us the term B C bar, and this horizontal one gives us the term A bar B. So now if you go and look at these two, it is not quite apparent whether there is anything common at all. You notice here, at least in the previous one there was a term AB which was common to both. Here we have A bar B bar, you do not have A bar B bar on this side. Then you have AB C bar, you do not have ABC bar on this side, instead we have a BC bar, right. So it is not immediately clear where the sharing is coming from, right. So if you do not do any sharing, you will need 7 AND OR gates plus 5 inverters. So you will need 3 inverters for this side, 2 inverters for this side, and you will need 7 either AND or OR gates. So in fact you need 2 OR gates and 5 AND gates, but you can do something slightly better. So you notice that we earlier had grouped these two together, right. We had grouped these two together, resulting in a term called BC bar. So now if you do not group it and if you leave it as it is, you would have got A bar B for this term, and this should have remained as ABC bar, right. And this is interesting. So we when I talked about K map, I always said you should go and maximize the number of ones that you are grouping, and the argument is if you maximize the number of ones that you are grouping, the number of literals go down, and therefore the number of AND gates will go down if you are doing a product, sum of products. So if I group 8 ones together, then I am knocking off variables, right. So this is something that we saw earlier, we will knock off variables if we group 8 ones together. However, here I am making a case for not doing maximal grouping. So this one was not grouped with this one, instead if you keep it as a loner, then you have A bar B bar plus ABC bar for this one, and for this one you have A bar B plus ABC bar. Now with sharing you can see that first of all the inverters go down in number, so you do not need A bar and C bar on both sides. So you need 3 inverters, one for A, one for B, one for C, so you get 3 inverters, and otherwise this term requires 2 AND gates. So remember A, B, C bar is 2 AND gates, so 1 AND gate here and 1 AND gate for this one, and this one requires 1 AND gate, this one requires 1 AND gate. So that is 4 AND gates plus 2 OR gates plus 3 inverters. So we have reduced the hardware cost by 1 AND gate. So the general philosophy of doing multiple output minimization is look at the ones of each function that are not ones of the other function, these must be covered. So you go to this example, you look at ones, for example these 2 ones here are not here and these 2 ones here are not here. So there is possibly no sharing that you can have with them anyway, right. So this term is only for F and this term is only for G, you can't do anything about them, you have to have those terms anyway. So that is the first bullet, look at the ones of each function that are not ones of the other function, they must be covered, and then start looking for the terms that can be shared. And when you do that, so for example you see that this term can be shared here and here. If I had not been careful I would have grouped this, however if I see that it is being shared, maybe just allowing for sharing is better than cutting down the hardware only for G, but you will still have that number of gates for A. So it is better to make only one copy of this term here and leave it as it is. So a few more examples here. So in the left side we have a function on 4 variables A, B, C and D, and the right side you have function on 4 variables again on the same inputs A, B, C and D, 2 different sets of terms. And if you notice you have these ones, the red colored ones are unique. So these 3 ones appear only in F and these 6 ones 1, 2, 3, 4, 5. So these 5 of them appear only in G. They are unique only to their respective outputs. So what we can do is we can start with the red ones first. So this is a red one and these 2 are red. We will start grouping the red ones first. So you have all these ones and these 2 taken care of, similarly these and these taken care of. So you do maximal grouping if you can for the red ones here. So all the red ones are now taken care of, they are peculiar or unique only to those, and after that you are still left with 2 of these ones, and if you notice these 2 ones are also in the same position in G. So I do not have to make a separate circuit for this term and a separate circuit for the same term in G, I can instead share that circuit. So what we have is, in terms of an expression, we have A C bar D bar, which comes from one of these terms, and A bar B D bar, which comes from the other term, but the common red term is B C bar D. On the right side, we have a quad here that gives us B C, we have a group of 2 which gives us A bar B bar D bar, and we have B C bar D, which is common. So with sharing, we actually get 7 gates and a total of 20 gate inputs. So the number of inputs that come into the gates is actually 20. So you ignore this for a while now, you need only 7 gates in this. So this is a very useful thing to have. So without sharing, you would have had 8 different gates. So let us just leave this for a while. You can see that B C bar D being shared is useful. So these are some do it yourself exercises with some marking already made. So we have 2 sets of min terms here, and the ones in red here and the ones in red here are unique to F and G, but the ones in blue are actually common across F and G. I want you to go and think about how you will do minimization for this. So there is another exercise which is on 3 different outputs. So this is slightly more tricky. So you have to now see what is common across several outputs. So I earlier said you go and look at what is shared between F and G. Now we have 3 different outputs and the truth table is already given. I am also going to give you the groupings. So the various groupings are given to you. Right? These are the groupings that are possible, and I would like you to go and think about what do you want to share across what and so on. So there is some color scheme that is used here for sharing. So I would like you to go and think about why that color sharing makes sense and what is the impact of that grouping. Go and count the number of gates that you have for each one of them. So in essence, what we have done in this lecture is we looked at the case for sharing terms across different outputs in what are called multiple output functions. So minimization of the terms in the presence of multiple output functions is not an easy task. So sometimes if you share it's better, sometimes if you share it's actually going to be worse. So you have to be careful about when to share and when not to share. In general, beyond a point this becomes very cumbersome for human beings to actually go and do what is called optimization. So if you want to go and look at the smallest number of gates that is needed to implement this 4 input 3 output circuit, it may not be possible at all. Right? We may not be able to get the optimal one for every single combination of 3 outputs and so on. So instead what we actually start looking for is we start looking at synthesis of circuits. Synthesis means we want to create a gate level description of these truth tables. However, we may or may not have the smallest number of gates. So this getting the smallest number of gates is not always possible. This is actually hard even for a single output case, but even when you have multiple outputs this problem is not easily solvable. It is a hard problem to solve. Instead we go and try and minimize as many as possible and not necessarily look for the optimal number of gates or the absolute smallest number of gates. We may not look for that at all. Right? This brings me to the end of module 11 of week 2, and in module 12 we are going to see, so we will conclude this week with module 12. Thank you very much.